Okay, so today we continue with the notion of differentiability. So in the previous lecture, I gave the definition basically of derivative of a function and the notion of differentiability, okay, at some value a or defined on some other. Today, we will see how to calculate derivative and so let me start with basic differentiation formulas. So, what is more easier than a constant? Nothing. So let's start by a constant. So derivative of a constant function. All right. So we consider C a constant, that is a real number for us, and we can show that what is the derivative. So here I use the Leibniz notation. The derivative of this is 0, and here is the proof. Okay, so how to prove this? Now each time you need to come back to the definition, right? And what is the definition? Well, it will be the limit when h goes to 0 of, if you remember, f of x plus h. So here the function is constant, so it will be basically c minus f evaluated at x, so it will be again c and divided by h. Okay, so basically you find that this limit is equal, so it's not an indeterminate, it's actually 0. This is always equal to 0. And you want to calculate the limit when h goes to 0. So this is 0. Okay. As you can see, the proof is elementary. Now, what is derivative of x to the n? Well, so the result first, the derivative of x to the n will be equal to n times x to the n minus 1. And the proof of that goes like this. So we calculate the limit when h goes to 0 of x plus h to the power n minus x to the n divided by h. Okay, so you have to basically expand this. If you expand this, you can show that, well, you will have a factor in x to the power n. Then the second highest degree will be something of the form n times x to the power n minus 1 times h. Then you will have some term lower degree. So the next one actually will be n minus 1 divided by 2 x to the power n minus 2 and then h square. And you go on like this. The last term being actually h to the n. So no degree in x, okay? And so this is the first term. And then you have minus x to the n, and you divide everything by this h, okay? Now, what happens is the following. As you can see, this term, x to the n, and this term will cancel out, and you will have, so as you can see, you will have only terms with the h in factor, h squared, and it goes to h to the n. So you can actually divide, cancel out this h, and you will get the limit when h goes to 0 of, so here this will be the term that will remain, n x n minus 1, okay? And I cancel out this h with this h, because this is an h. And after that, I will have some term that I can factorize by h. So the next term will be h n times n minus 1 divided by 2 times x n minus 2, etc., etc. And the last one will be h to the n minus 1. Right. But the important thing is that because we can factorize here by h, and h goes to 0, all this will go to 0. And what will remain is therefore n times x to the power n minus 1. Okay. Good. So, I won't prove it, but in fact, more generally, we can see that the derivative of x to the power alpha, so the power function, as you remember, is defined like this. You define first for integers, okay, integers, and then you define it for rational, and then you say that rational are approaching the real number, so you pass to the limit. This is how basically you should prove this kind of assertion. So x to the power alpha, where alpha is any real number, what will be this derivative? Well, you can show that this derivative will be, as you expect, alpha times x to the power alpha minus 1. Okay, so this is true, in fact, for any power function x to the power alpha. Now, next, so let's apply this, for example, in the case, example, dx to the power half, right? That would be that. Well, if you apply the function, it will be 1 over 2, okay, which is alpha, times x to the power minus over 2. So half minus 1 is minus half. And, okay, so this is, as we have seen this before, this is 1 over 2 times square root of x. This was showed before. Okay, now next formula. What is the constant multiple rule? Okay, by this, what do I mean? I mean that I'm considering C a constant, a real number, and F a differentiable function on some open interval Okay, so basically the rule is saying the following. What happens if I'm doing C times the constant f and I want to calculate its derivative? Then this is very easy. This will be just C times the derivative of f. That's right. I let this, the proof of that as an exercise. Very easy. And next comes the sum or difference. So basically, as you can see, we revisit the limit laws. Okay, we do kind of limit laws, but this time for differentiability. So what is the sum or difference rule? Here again, we take f and g, two differentiable, let me abbreviate this like this, differentiable functions on the same open interval. Then I want to calculate d of f plus or minus, right? I want to calculate this. And not surprisingly, if you assume that both functions were differentiable, then the plus minus of this will be df dx plus minus dg over dx. Okay, so nothing surprising in this. Okay, that's right. Yeah, let's have a look at this proof here. Okay, how do you prove this kind of statement? Right. So again, we want to consider the following limit: the limit when h goes to 0, or of f plus or minus g x plus h minus f plus or minus g evaluated this time as x and everything divided by h. Yeah, we want to calculate this. So basically, we are going to cut this into, so we can write that this is limit when h goes to 0 of, yeah, here we really use, so limit laws, right? This is really the application of limit laws. The limit of a sum or difference is the sum or difference of the limit, and therefore we can really write this as fx plus h minus f of x divided by h plus or minus the limit when h goes to 0 of gx plus h minus g of x divided by h. You see, it's just another arrangement of the different terms, as you can see. And this is, of course, df over dx plus minus dg over dx. Yeah. So you prove it. You reduce the proof of this law concerning differentiation formula actually to the limit laws. Okay, so this is the same statement, basically. Let me set another exercise for you. Exercise. So find the points on the curve y equal x to the 4 minus 6x to the square plus 4, where the tangent line is not vertical. If it was vertical, it means infinite slope, not differentiable. But here we just want to know where the tangent line will have will be horizontal. Horizontal. Okay. So I'll let you think about this. Next formula we want to study today. What are the derivatives of sine function and cosine? Sine and cosine. Okay, so the result is as follows. Basically, the derivative of sine function, this is equal to the cosine. And the derivative of the cosine is actually minus the sine function. Okay, so let's see the proof of the first statement. And probably I will let you use the proof of the second statement in the exercise. So proof. We want to study this derivative, right? Sine prime. So by definition, this is definition, this should be the limit when h goes to 0 of this limit, x plus h minus sine of x divided by h. Okay, so here we are going to apply, so we can expand, as you know, the sine of x plus h. Okay, what is this? So sine of a sum is, as you remember, it will be sine x times cos h plus cos x times sine h. So all these trigonometric formula, we assume in this class that you know them. So please remember them. And so I have to do minus sine x, and then I divide by h. Okay. Now, what can I do? I'm going to write this a little differently. This is the limit when h goes to 0 of sine x and times. So here I have cos h minus 1 here, 1 times sine x, and here divided by h. And what remains will be the following, plus cos x times sine h divided by h. Okay. Now, how can we calculate these two limits? So, basically, I'm going first to, so this we have calculated this actually. When h goes to 0, this goes to 1, okay? So when h goes to 0, we know that this will go to cos x times 1, if you prefer, okay? This was already studied. But what about this limit? Here is a little delicate because direct evaluation doesn't work. As you see, we will get cos h when h goes to 0 will be 1, 1 minus 1, 0, divided by 0. This is so-called indeterminate, so we need to write this differently. So we need to calculate the limit when h goes to 0 of cos h minus 1 divided by h. Okay, this is not trivial, but here we are going again to use famous trigonometric formulas. So if you know very well your trigonometric formulas, then you remember that 1 minus cos 2x is equal to 2 times sine to the square of x. And therefore, I can, if I set 2x equal h, then I can rewrite this formula as cos h minus 1 equal minus sine to the square h over 2, right? Yeah, so this is this value here, the nominator, that I rewrite in this way. And therefore, I can now calculate my limit when h goes to 0 of cos h minus 1 divided by h. What is that? Well, this will be, therefore, the same as doing the limit of minus sine to the square of h over 2 divided by h, isn't it? But h, I can of course write it as h over 2 times, or here, 2 times here, okay, like this. And now I can continue to transform this writing to make it clearer, even clearer. So yeah, let's not close this bracket here, I will close it later. So here we continue. We can write this as minus 1 over 2, right? And then we will have sine to the square, so it means 2 times sine h over 2 divided by h over 2, okay? And another one, sine h over 2. That's right. And now we are ready. Now we can close, because everything is clear. When h goes to 0, as you can see, this doesn't move, it will be minus half. This goes for the same reason to 1. So minus 1 over 2 times minus 1 times, what is the limit of this? Limit of sine h over 2 when h goes to 0. So it's a continuous function, we know. So it's a direct evaluation. And sine of 0, what is sine of 0? It is 0, okay? So we get finally the limit of all this is 0. Okay, to summarize, okay, therefore, the limit, so sine prime is equal to basically cos x. Okay. This is the conclusion. And basically, I'm going to let you in exercise the second assertion. So exercise prove that the derivative of cos function is minus the sine function. Okay? The proof is completely analogous. You will use different trigonometric formulas. All right. Now, another formula is the product rule formula. How does it work? So, what is the derivative of a product of functions? When this goes like this, it will be equal to f of x times the derivative of g of x plus g of x times the derivative of f. So you can write it f g times g prime equal f prime g plus f g prime. Okay, one of these two formulas. And yeah, the proof is quite interesting also. So let's have a look at the proof. Okay, so how do we prove that? Proof. Here we want to calculate the limit when h goes to 0 of the following: f times g apply at the value x plus h minus f times g apply at the value x, and we divide everything by h. So the game is to really rewrite this. Yeah, so remember here f and g are two functions that are differentiable. Okay, differentiable. So we know already that we can calculate their derivative. So f prime exists and g prime exists. Now the game will be to rewrite this in terms of this f prime and g prime, isn't it? So here is how you can do that actually. So this will be equal to what? It will be equal, in fact, to, so I'm writing this like this: f of x plus h times g of x plus h. So this is basically the meaning of f times g apply at x plus h. It means this. It means it's f of x plus h times g of x plus h. And now I'm going to write like this: minus f of x plus h times g of x. And I'm going to So I retract this, I'm going to add it immediately, f plus x plus h times g of x. Okay, so I've done, this is 0, right? I've done nothing. And I have to do minus f of x times g of x. That's it? Yeah, so far this is the same. Now, let me see. Oh, yeah, sorry, I forgot to divide everything by h, right? So this is all divided by h. Right. Now, yeah, I'm going to put f of x plus h in factor. So if I do that, I will have g of x plus h. This is given by this term. And then here minus g of x, okay? And here I can divide by h. Then this is a first term, that is quite nice. And if I do that, I get plus g of x, this time I factorize by g of x. And using this, I will get f of x plus h minus f of x, and here again I divide everything by h. Okay, so what? So this is the same as this, which is the same as this. Okay, so I'm really calculating this here. Now I close the bracket here. Okay, and I put h going to 0. So h goes to 0, and here h goes to 0. What is happening is the following. F of x plus h, when h goes to 0, this will go to f of x. You see? And this, because I assume that the function g is differentiable, this exists, and this goes to g prime of x. Right? Plus, now what happens in here? Well, h goes to 0, this term is constant, does not depend on h, so it will go to g of x. And what happens inside the bracket? Well, as you can see, this is by definition the derivative of f. And therefore, I get my formula. So this, I remind you, was fg prime of x. And I get this is f of x times g prime plus g of x times f prime. So as you can see, the proof is to start by the definition and rewrite the content in terms of the derivative of f and derivative of f prime. All right. So, quotient rule. Quotient rule. Well, quotient rule is basically same. So what is derivative of f over g dx? Well, it's slightly more difficult because you have to remember a minus sign. So it will be g of x times the derivative of x minus f of x derivative of g over dx. And everything divided by g of x to the square. Yeah, so it's a little complicated, or you can remember this formula. What is f of g prime? This is g f prime minus f g prime divided by g squared. Yeah, remember one of the two formula. The proof is similar to the product rule. Okay, so I leave this as a nice exercise to you. All right. Now, very important rule is the so-called chain rule. Chain rule. All right. So here the statements. So we consider f and g two differentiable functions. And f composed with g. So f composed with g. So basically f will go from A to B, right? And g will go from B to, so this is the opposite. Here I basically want something, g will go from A to B, and f will go from B to C, right? Then, by composition of function, I mean the function that start from A and that end up in C to value x, I will apply the rule, composition rule. So I will set this to f evaluated at g of x, okay? And we assume that this is well defined. Then f composed with g, the function is also differentiable. And we have f composed with g prime evaluated at x. This will be f prime of g of x times g prime of x. Now you can use the Leibniz notation, and this is really, especially for this chain rule, that the Leibniz notation is so powerful, as you will see. So we set y equal f of u, and we set u a function of x, okay? Then this formula is just saying the following. We are looking at the derivative of y divided by dx, okay? So y is a function of u and u a function of x, and we want the derivative of y with respect to x. And the result is that is basically, first you derive by the variable u, and then you multiply du divided by dx, okay? So this formula is extremely easy to remember, isn't it? Because morally speaking, we cancel out by du here, okay? So this is just a notation, but it makes this formula here very understandable. Yeah, of course, dy over dx is dy over du times du over dx. It's because, morally speaking, we cancel out by du. So, as you can see, it's very powerful notation. Now, what is the proof of this? So, the proof is, again, to start from the definition and to reorganize the writing of it. So, here I'm going to use the other limit, okay? So, if I study differentiability at A, for example, so I want to understand what is f of g of x, right? Minus f evaluated at ga, and divided by x minus a. And the way to do that is to basically rewrite this slightly differently. Okay, so we are going to do it like this. First, I'm going to write it first term, so f of gx, and then minus f evaluated at ga. This doesn't change. I'm going to here divide this by gx minus ga, right? So in my head, I understand, I set u equal gx, you see? So it will be f of u minus f of ga, and divided by u minus ga, okay? Times, okay, if I do that and I want to find exactly the same thing, you have to multiply this time by g of x minus g of a, and divide by x minus a. Okay, but now I can really apply the product rule. Product rule will work very well, because this goes to, when x goes to a, this will go precisely to f prime of g of a, right? And this will go to g prime of a. Okay, so this was the calculation of f times g, f composed with g, and it was evaluated at a, right? And I find this is equal to f prime evaluated at g of a times g prime of a, which is basically the evaluation of this formula setting x equal a. So this is the proof. Yeah. It works beautifully. If I apply this chain rule, many times I can conclude, for example, as a corollary, small corollary is that f to the power alpha, and if I differentiate this will be equal to alpha g to the alpha minus 1 and times g prime. Yeah. Yeah, I can conclude, oh sorry, not g but f. That's right. Next rule, let's calculate the derivative of an inverse function. Okay, so here we take f from a to b. So b is equal to the range of f, okay? We assume that, and we assume that f is 1 to 1, 1 to 1. So if you remember, when we have that, we know that, okay, so let's say, so this x will be sent to some y equal to f of x, and if I evaluate, for example, at some value a, this will give some b. Then, if I do that, I will have an inverse function, if you remember, that goes from b to a, and that will send y to x and my b to a. Now, I want to calculate when the inverse function exists, its derivative, okay? So, the statement goes like this. Assume that f is differentiable at f minus 1 of b, which is, under my notation, a, right? So if we assume that f is differentiable at f minus 1 of b, then, and, sorry, we have also to assume the following. f minus 1, we assume that f prime of f minus 1 of b is not 0. Okay? Then, what is the derivative function of f minus 1 evaluated at b? This will be 1 over f prime of f minus 1 b, which is 1 over f prime of a. Yeah, so basically the proof is very easy. So basically we want to calculate f minus 1 prime at b. So by definition, this is the limit when y goes to b of f minus 1 y divided by f minus 1 b, and this divided by y minus b, right? But this is actually, okay, if I open the bracket here, I can rewrite this as, so f minus 1 of y will be x, right? F minus 1 of b will be a, x minus a, and this will be just f of x minus f of a, right? And I want to calculate the limit of this when y goes to b. So, sorry, I'm going to rewrite here. This is the same because y is basically f of x. This is the same as studying the limit when x goes to a of this. Okay, and this is indeed 1 over prime of a, which proves the formula. Okay, formula here. With this rule, this formula, you will be able to calculate the inverse limit of all inverse trigonometric functions. So it can be quite useful. All right, I will finish. Yeah, I have a few more rules to talk about. For example, the derivative. Yeah, we have not seen this one yet. Derivative of exponential and logarithm. Okay, so here I write theorem because it's not totally obvious. In fact, the derivative of the logarithm is 1 over x. And the proof of that is that if you want to calculate this, this is by definition the limit when h goes to 0 of ln of x plus h minus ln of x divided by h, isn't it? And again, I'm going to work out this writing and write it slightly differently. So first of all, I can apply the laws of logarithm. This is the same as studying the, so the ln difference of logarithm is the same as doing this, right? Logarithm of x plus h divided by x, and then this is over h, right? Now, if you try to, you cannot do a direct substitution here because you will get really indeterminate 0 over 0. Why is that? Well, as you can see, this will go to ln of x over x, which is ln of 1, which is 0, over h 0. Okay, so it's not good. Now, if you, so we transform this as follows. We consider the following limit when h goes to 0. I can write this as follows. So I'm going to do 1 over x and then because this x doesn't exist, I have to cancel out immediately, x over h, and then I rewrite this x plus h over x. I can write it, in fact, as 1 plus, 1 plus h over x. Yeah, this is the same. X over x, 1 plus h over x. Right. And here we go. Now, this is equal to 1 over x, limit when h goes to 0 of logarithm of 1 plus h over x. So this is another rule of the logarithm. If you have a constant here, you can put it in factor here. So h over x. Right. Now you can calculate the limit. This is 1 over x times the limit of this. Now this goes to e when this was a definition actually of e when h over x goes to 0, which means when h goes to 0, right? This converges with e, and so ln of e is 1, okay? And you get your formula. So this is the proof, and as a corollary, you can show that the derivative of the exponential, this is equal to the exponential, and for the proof I let you, this proof will be let in exercise. And so how will you prove this? You use the inverse function formula. Okay, we have seen the derivative of the inverse function, and it happens that exponential of x is the inverse function of logarithm. Therefore, if you know the derivative of logarithm, then you can deduce the derivative of its inverse function. All right. The last rule I want to talk about today, well, it's more like a theorem. It will allow you to deduce derivatives. Derivatives is a calculation of a limit, okay? And limits are quite tough to calculate. This is a very nice tool actually to calculate limits, and it's called L'Hospital rules, from the name of a mathematician called Mr. L'Hospital. So let's see this rule, L'Hospital rule. So L'Hospital rule will give you a very nice way to calculate limits using derivative function. But the hypotheses are extremely important for this rule. So assume that, so basically we have two functions, f and g. They are differentiable. And g prime of x is not 0 near a, except, differentiable at some value a, okay? And g prime of x is not 0 near a, except possibly at a. Okay, so it's not that bad condition, because g prime of x could be 0, but you really want that g prime of x, when x is near a, won't be 0, okay? Then, so we assume that, and you have a third condition. So remember, you have three conditions. Huh? This is one, condition 1. F and g are differentiable at some value. This is condition 2. G prime of x is not 0 near a, except possibly at a. And condition 3, you will assume that the limit when x goes to 0 of f of x will be equal to the limit when x goes to 0, a of g of x, and they are both equal to 0 or plus or minus infinity. Yeah. Then the conclusion of L'Hospital rule is that the limit when x goes to a of the quotient f of x divided by g of x, this will be actually equal to the limit when x goes to a of f prime x divided by g prime x. So remember that for direct substitution, if the value g of a was 0, then you were not able to calculate this. But with L'Hospital rule, you can go to the derivative and it will give you the same limit. The only very important thing is that you need to remember, before applying this L'Hospital rule, you will need to check imperatively 1, 2, and 3. Okay? So let me give you an example. So imagine that I want to calculate the limit when sine x over 1 minus cos x when x goes to pi minus, yeah. So I apply L'Hospital rule immediately without checking 1, 2, 3, okay? Then what happens is the following. This will be the same as studying the limit when of cos, okay? The derivative of sine is cos, and here, what is the derivative of 1 minus cos? Well, it will be derivative of 1 is 0, and minus derivative of cos is minus times the derivative of cos. That is sine, isn't it? Yeah. So, now what is this? This is, as you know, cos x when x goes to pi is minus 1, and pi minus 1, right? Pi minus 1. So cos is here, I will be here, right? I will be near minus 1. And this sine x, this will be 0 plus, right? So 0 plus divided, so this will be minus 1 something plus, and divided by 0 plus, right? So this will be minus infinity, isn't it? Minus infinity. Yeah. Unfortunately, but this is wrong. This is wrong. I applied stupidly L'Hospital rule, okay? And I found that the limit is minus infinity. But let's have a look. What is sine evaluated at pi minus 1? Yeah, as I said, this is something like 0 plus. And now what is cos? This is minus 1 plus. So 1 minus 1, yeah. Ah, yes, this is minus 1. So, in fact, direct substitution works here. Yes. So it was not obvious, but look at that. The limit when x goes to pi minus 1, this will go to minus 1, and here we will go to 1 minus minus 1. So 1 minus minus 1 is pi. This was 0. Yeah, this was 0. Yeah, I'm a little tired now. This is 0, and 0 over minus minus is 2. So 0 over 2 is 0. This is totally well defined. If you apply direct substitution, you will find that the limit is 0. This is the answer. The real answer is that this limit is 0. What was wrong here? What was wrong? Well, third was wrong. Third was wrong. Direct substitution was giving us a 0 over 2. It should have been 0 over 0 or infinity over infinity. Okay? So the condition 3 was wrong, and applying hospital rules was giving the wrong answer. So be always very careful when using this hospital rule. Okay, I finish here. Thank you.